The t-test has a few variations, and you've probably seen these before. The name the t-test actually comes from the distribution that we compare the test statistic with, which is student's t-distribution, which looks very, very similar to a normal distribution, except that it has what we call slightly fatter tails. So you're welcome to look up fat tails when you're bored on Google. So the variations are, we can test if a single mean is equal to a particular value. This is quite uncommon because it's a very simple test, and so you won't see this too often by itself. It can form part of an omnibus of tests for something else, and we will see it when we look at regression and some other things. More often it's used to see if paired measurements are equal, so this might be before or after measurements where they are matched or paired across a person or across some other characteristic. So that would be called a paired t-test. It can also be called a dependent t-test, and it uses matched data, but I don't think I've ever heard it called a matched t-test, although I don't see why you couldn't call it that if you wanted to. And then the last one is testing if the means of two independent groups are equal. So this might be if we have, say, a treatment group and a control group, and this is called an independent t-test. So for example, if we think about this hand group study, we might want to test if the mean age is the same in the treatment group as in the control group. And this would be part of checking if there are any problems with the design of the experiment. You can quickly pause and refresh your memory on that study if you haven't watched the first video, or if you've had a bit of a break. So the process for hypothesis testing, the first step, we want to work out what is the dependent variable for this test. So this is not the main outcome of the research study, it's just the outcome that we're interested in for this test. In this case, the dependent variable is age, and this is continuous. And we want to know if age depends on something else, or is age the same in both the groups? We could phrase it a number of ways. So is the mean age of the comparison group equal to the control group? So this suggests then that the independent variable is the treatment group, which is categorical, and it's nominal, but that doesn't matter too much. In this case, there's a comparison group and a control group. We've got two separate or independent groups. So there's no person which is in both groups and they haven't had a before and after measurement or anything like this. So we're after an independent t-test. So if we look at the flowchart, we would follow this down from starting with the dependent variable. We're looking at, we've got a continuous outcome. These are the assumptions we're going to check, and we'll do that in a second, but the first thing we want to do is choose an appropriate test. So these are our choices in this column. We don't have paired data, we don't have lots of groups, we've got two independent groups, so we're going to start with the independent t-test. Now we're going to check the assumptions for this test, and if they are not met, then we might slide on across here to the MAN-U instead. So the next step then is to see if our data meets the assumptions, and I've put links in the up the top to the Laird statistics page, which lists these out. It's a very useful web page. I do encourage you to read it. They give a little description of the test, these assumptions, and then they walk you through an example, so you get to see another example if you want to. So the assumptions are that your dependent variable is measured on a continuous scale. Yes. Your independent variable should have two categorical independent groups. Yes. You should have independence of observations, which means that there is no relationship between the observations in each group or between the groups themselves. So this is something to do with how the study has been designed, and it's not something that we can check in most cases statistically. But we want to know that each person is in fact an independent observation and not reliant on some other person in the group or related to some other person or observation in the group, which might sort of bias the results. So in this context, we would probably want to have people perhaps that were definitely independent of each other. So we might not want two brothers in the study because they might have similar outcome, or equally two sisters. And when we've been surveying houses, particularly in the initial baseline survey, I said that we only wanted to survey one person from each house because quite often people in the same house will have some similar behaviours. So in order to get the best representation of the town overall, let's pick one person from each house so that we don't get any clumps of data. So this is down to the methods. It's not something we can test, and it's hopefully a reflection of a good design. So these first three assumptions are about checking that we have appropriate data, and the next three we would actually test using some software, or have a look at using some software anyway. So these are that there should be no significant outliers. The easiest way to check this is simply to do a graph, that your dependent variable should be approximately normal for each group. Again, the easiest way to do this is simply to do a graph. There is a test of normality, but I don't require you to do it. It's not what I would call a really strong assumption. If it's a little bit not normal, usually the test will still work. So looking at a graph is fine. And there needs to be homogeneity of variances. So what this means is that we're expecting a similar amount of variation in both the groups. Now, this is another thing where if there's a little bit of difference here, it might not matter. And we can actually select some options as a part of the test to adjust for this and do a variation if it's not true. So again, this is not really a deal breaker either. It's what we call a very robust test. If we want to test the means, this is usually a good way to do it. So if we think about the outliers first, box plots are a great way to look for outliers. In this case, there are no outliers. They would get marked with a little asterisk or a circle, depending on how far away they are. I can't remember offhand the calculation that SPSS does. It might be if it's more than 2.5 standard deviations away from the mean, or even maybe more than 3 standard deviations away from the mean, it gets marked as an outlier. I mean, you can look that up if you're really interested, but for the purposes of this course, we'll just do some box plots and we'll have a look. So this assumption's fine. And the reason that we need to be careful about outliers is because they can pull on the mean. Outliers can have quite a strong effect on the mean, which is what we're testing with a t-test. So if you think about a seesaw, if you've got like lots of little kids along the seesaw, if one of them moves around, it doesn't make too much of a difference. But if then one of the dads or a really heavy person jumps on one end, that's like an outlier. They're really unusual and they'll really pull that balance point around, which is the same as the mean. So we do have to be a little bit careful about outliers. If you have outliers either side, that's like you've got two dads jumping on the seesaw, one at either end, and they kind of cancel each other out. So sometimes you can have a couple of outliers and it doesn't even matter. So that's a case-by-case, just judgment call, I guess, and we'll do some practice in the workshops of that. Histograms are good for looking at normality, so this was the next assumption. And to get this in SPSS, you actually have to go through the legacy dialogues. It's not in the chart builder with the rest of the tests. You don't have to do a formal test of normality. Now, one of the problems with small sample sizes is that they don't always look normal just because you don't have enough data. So in this case, it's probably okay. Like this one kind of looks all right. And this one here, it's looking a little bit chunky, but it's possible if we rebinned that or put this in wider divisions, it would look fine. There's nothing here that really concerns me too much. I'm not sure if I did rebin it. No, I didn't. So the bins are the way that we divide up the data, and we'll have a look in class at how we rebin this if we want to take another look at it. And then that last assumption was the homogeneity of variances. So this is about saying, do we have a similar spread of the data in both the groups? And we can see that they are spread out a similar amount. But there is a test for that pops out when we do the t-test anyway. So there are three tests presented in the output. This first box here is just giving us the means and the standard deviations, and we probably do want to know these. If you remember, these were reported in the table 1 of participant characteristics. So if we were drawing this up, we would want this information. When we get down to this test, I just can't quite remember what's on my next slides. Yeah, I've broken it up. You'll see that we've got the test for equality of variances, and then we've got two versions of the t-test. One if we have equal variances and one if we don't. And quite often you'll get the same answer either way, so it's not too much of a problem. So let's have a look at this test for equality of variances. So the null hypothesis in this case is that the variances are equal. I was thinking I needed my pointer. And it's actually being compared with an F distribution, so it gets this F here, but we would call it a test of variances. This is the test statistic. The significance is the p-value, and this is a really high p-value. So the null hypothesis is that the variances are equal, and we have got no evidence against that. So the p-value is the probability of observing the data if that null hypothesis is true. So the probability of getting data that looked like this, if the variances were in fact equal, is about 85%. That's a pretty high probability, so this is fine. There's no reason to suspect there's anything wrong with the data or the hypothesis. So we've got no evidence that the variances are not equal. And I'm aware that this sort of double negative, that we have no evidence that they're not equal, is problematic for some people. It takes a little while to get used to. But I'd prefer to write it in a correct way, and if you want to think about it a little bit differently, that's okay. So we've got no evidence that they are different. Therefore, we will assume that the variances are equal for the purposes of this t-test. So this was for that last assumption about homogeneity of variances. The next part, after the test of variances, is the t-test. Now, I have a feeling that in the latest version of SPSS, it actually splits this out into a different table, which is quite handy, but I don't think that is installed on the labs yet, so yours will probably still look like this. So this, if you were doing this test by hand, you would calculate the test statistic, which is this t-value. You would calculate the degrees of freedom, which is related to the sample size, and then you would look up your p-value off some tables. And then there's another version of the test below if the variances were not equal. So here we have a p-value of 0.72. So we have no evidence that there is any difference in the mean age between the groups, which is what we want because we're hoping that our groups are approximately equal. Now, if the assumptions were not met, that's when we could have used the Mann-Whitney U-test instead, which is a non-parametric test because it doesn't assume the data is normal and it doesn't compare the means. You can compare the mean ranks, or you can compare the medians, and we can compare the shapes of the distributions. So we can do other things if we don't want to test the means. In this case, we don't need to use that. So the null hypothesis is that the mean age of both the groups is the same. The chances of observing this data if there was no difference in the mean age between the groups is 0.742, which is the p-value. Therefore, we have no evidence that there is any difference in the mean ages between the groups. So in terms of the design of the experiment, this means it's unlikely that there is any potential for confounding due to age. So this is a good thing. And then we would write our conclusion. And if we were formatting this as a sentence, we would say there is no significant difference in the mean ages of the two groups. And I've put in the test statistic and the p-value. And we would probably also put in the mean ages and the standard deviations or a confidence interval as well if we were fully reporting it. In this case, that's been put into a table, so we don't really need to write that down. So in terms of what they have in the paper, they have, where they've tested age, they've actually got an F statistic because they've done a slightly different test. You'll find that in many cases in statistics, which is really irritating to a lot of people, that there's more than one way to skin a cat. So they've done something a little bit different. We're sticking with the t-test, but you'll see they still come to the same conclusion. They still get a high p-value and that there's no difference between the groups. So the second example from this paper might be in testing the outcome. Is there a difference in the hand grip strength between the two groups? So H0, there is no difference in hand grip strength between the comparison group and the control group. where the comparison group were the ones that were getting this social age-based comparison, and we're expecting that they might perform worse. The hand grip strength is a continuous measurement measured in kilograms, and we still have 2 independent groups, so we can actually do this using exactly the same process. If we do a box plot, we'll see that there, whoops, didn't mean to do that. We'll see that there's one outlier. Now, depending on how far away it is, it'll either get an asterisk or a circle. This little number here is actually the row number that it's on. So if you're wondering, gosh, who was this person who was so strong? Then we could go and look up line number 28 and see who they were. So this person is not just strong for his group, he's actually stronger than everyone else in the whole study. So sometimes you might hear that you should exclude outliers, but I think that's a really bad practice, because I think there could be some valuable information in the outliers, and it's more about understanding who is this person, why did this happen, and do they represent some part of the population who we haven't adequately represented with the rest of the people. And then we would go back to the design of the study and think, well, how were these people sampled and found, and how representative are they? If we're worried that they're having an impact on the results, then we could actually temporarily take them out, run the test, see what the results are, and then see if it made a difference anyway. Sometimes there is a justification for excluding a truly unusual person. Perhaps they don't meet some criteria and that wasn't realised till later, or they do represent a very different demographic that needs to be studied differently. I know once I had students who were doing a project, and this was for a different course where we used to get them to do any project they like, and they went out fishing and they were looking at the length of different fish, and they caught all these fish that were quite little, and then one of them caught a shark at the end, and this shark was so much bigger than the rest of the fish. It really just messed up. I can't even remember what they were looking at with the fish, but it just messed up the rest of the data. And so in the end, their justification was, we were really interested in cod, or I've got no idea, whatever they were fishing for. The shark was an accident. It might be interesting, but that would be a separate study to look at the lengths and weights or whatever of sharks, and so we're going to exclude it. So you can exclude an outlier if there's a justification for it. Otherwise, I would just leave them in and see if they're perhaps having an effect on the results. It's possible that in this case, this person will be dragging the mean upwards slightly. So you'd normally expect the mean to be roughly in the middle. This line is actually the median, not the mean. We might expect the mean is somewhere around here, but the effect of the outlier will actually pull the mean up, and maybe it would pull it up quite a bit. And we can see that the data in this case is actually not quite normal. And that's because we've got this truncation at 0, so you can't get hand grip strength less than 0. The t-test is fairly robust, and part of this will be caused by the fact that they've got fairly small sample sizes, 28 I think in each group. So we might be a bit cautious in our conclusions. We might not want to draw very strong conclusions based on this, but it's probably still okay to go ahead and use the test. So the conclusion when we run the test in this case, I feel like I've missed the output from the test. There's the output. I'm not sure why they were in the wrong order. Let me walk off to the side. So here we've got in group 1 and group 2, we have a mean hand grip strength of 6.9 and then 11 in the other group. Test for equality of variances. Now, this is very strong evidence that the variances are not equal. That's a low p-value, and so we would probably use the second line of the test in this case. And we do have some evidence that there is a difference in the mean. So this is the p-value, this is the test statistic. The probability of observing this data if the means was equal is nearly 4%, and that's pretty low, and it's less than this cutoff that we often use of 5%. So we would say that we do have some evidence here that there is a difference. Now, if we just look at these numbers, we might say, gosh, the difference from 6.9 to 11 is really big. How come that p-value is not smaller? And that'll likely be down to the sample size. We can't have really confident results if we've only got a small sample. So this p-value does show that we have some evidence of a difference, but it's not super strong evidence. And we can see how they've presented this in the paper. Comparison group 6.9 with the standard error, not the standard deviation. So that's the standard deviation, that's the standard error of the mean. The control group, and then this is the test that they did. We would have a t here and our test statistic. And the p-value, which you can see has come out pretty much the same, even though they've done a different test. This last symbol here is a measure of effect size. So there are a few measures that we can use to try and standardize whether or not effect sizes are small, medium and large, because then it makes it easier for the reader to say, yes, it was a small effect, a medium effect, a large effect, even if we're not completely familiar with hand grip strength. Now, we're not specifically covering that in this course. It's not something that it's easy to get SPSS to output. And also there are quite a few different measures. This one here is called partial eta squared. There's also eta squared, and you might see Cohen's d and a few others. So if you're interested in effect size, you can look these up and you can get some rules of thumb for how to interpret them. But we're not specifically covering this. What I would like you to do is look at the p-value and actually just look at the means and make a judgment call. Do you feel that this is a big effect or a small effect? Now, it might not be easy to do this for someone else's study where you're not completely familiar with what hand grip strength is, and maybe you don't know what a sort of normal person's hand grip strength is. But for your own study, you should have a better handle on what it is that you're measuring, and you should be able to make more of a judgment call about how big the effect was. So I'm just skipping back a page because I feel I've got those two slides out of order. There is good evidence that older people compared with younger people perform worse on a test of strength than those who are not subject to the comparison. And then we can put in the test statistic and the p-value. The comparison group performed on average 4.11 kilograms worse than the control group. So I've summarized the test, I've given a conclusion, and I've given a statement of the effect size by putting in what this difference was. So that's how we would write the conclusion for the test. And here I've got the details of how we chose which version of the test to use. So this is how they've written it in the paper. A little bit different because they've used a slightly different test, but you can see they're pulling out all the same key points here for theirs. So you can pause that and read that if you like. There's also a link to the whole paper if you would like to read that. So they discuss the flaws in the experimental design and how they adjusted for it statistically. So if you read the whole paper, you'll see they've done some statistical adjusting, and they've done some comparison with what the norms or the normal values are based on other studies. And then they've done all of this to say, look, we know there's problems with our study, we've made these adjustments, and then after we make these adjustments, we still come to this conclusion. The effect of the comparison remains significant. So they say even if they try and adjust for these things that are potentially wrong with their study, it still looks like there is a significant effect. So that's part of, in this case, because they've done more testing, that's part of the results section. But if they were discussing more generally about the implications of their study, then it would belong in the discussion. And a graph, which is always helpful, and we had a little look at this before. When we do these graphs, we won't be doing the bars. I prefer to keep bars just for bar charts. I prefer the means just to be represented with dots. That's just a personal preference of mine. I find that sometimes people get these mean and confidence interval plots or error bar charts confused with actual bar charts and then can do silly things. So that's why I prefer to draw them differently. And we'll see that in the workshops. Oh, no, I've got it here. It's always funny when you write your lectures that you use again the following year and you forget what you've done. So this is what ours will look like when we do them in SPSS, just a dot instead of the bar. And it's reversed them as well. We should put labels here. We know that this is the comparison group and this is the control group. So we should put a label here to make that clear to everyone else what that number means. And then they've written a plain language explanation of what this means. So we do the test, we write that statistical result, and then we write a plain language statement. A social comparison with younger people creates a threatening stereotypic expectancy that leads to underperformance and less persistence on the hand grip task. Given that age-based comparisons are frequent, if not endemic, in everyday life, it is likely that older people may quite often find themselves facing negative age comparisons, and consequently, many may also perform everyday physical tasks suboptimally and appear and believe that they are more dependent on help than is actually necessary. So I think that's a really great little paper. They made the data publicly available, which is fantastic. So you can actually download their data and have a look at it for yourself, and hopefully you can replicate the results that we've shown here.